Good morning, everybody. Thanks for coming to my talk. My name is Tsung-Wei Huang, and most people just call me TW. Today, I'm going to talk about dynamic asynchronous tasking with dependencies. And this is a project to help you parallelize your applications. This is what I'm going to do in today's talk. We are going to understand the importance of asynchronous tasking with dependencies and recognize some of the limitations of existing asynchronous tasking models. And then I will introduce a new dynamic task graph programming model called AsyncTask and show you how we overcome some of the scheduling challenges to support this model. And finally, I will demonstrate the efficiency of AsyncTask and conclude the talk. You probably already know parallel computing has advanced many of our application performance to the new level that is previously out of reach. For example, if you want to train a machine learning model, using 40 CPU, you can get 10x speed up. With one GPU, you can bring another 10x speed up. More importantly, modern hardware has been designed to run in parallel just for performance. For example, here I am showing you an Intel Haswell microarchitecture that has been released early in 2013. If you look at this architecture, it typically comes with 4 cores. It has one integrated graphic processing unit on chip. In terms of architecture, it is based on the superscalar architecture. So basically, it can issue and complete multiple independent instructions per cycle. It also supports hyper-threading technology that basically allows a single physical CPU core to appear as 2 logical processors to the operating system. So if you do not do parallel programming, then you are not utilizing your hardware efficiently. However, today's parallel computing problems are very complicated and irregular. Here I am showing you a computational task graph of a GPU-accelerated circuit simulation workload. This task graph models a GPU operation as an asynchronous task and a dependency between 2 GPU operations in an edge. Now, if you look at this computational task graph, it can be very, very huge. In this example, where we are simulating an NVIDIA deep learning accelerator design that has over 500 million gates in net, the resulting task graph has over 1,000 asynchronous kernel tasks and 1,000 task dependencies. Even with a GPU, it will still take several hours to finish. This is another example of highly irregular parallel computing problems where we want to parallelize a VLSI circuit timing analysis algorithm using many core CPU. The analysis algorithm is modeled as a task graph that propagates the timing values from the inputs of the circuit all the way to its output. For a very large design, the resulting task graph can contain more than 100 million asynchronous tasks and over 150 million dependencies. This is very, very huge. It turns out parallelizing this type of irregular problem is not very easy because you have to deal with a lot of technical details such as parallelism abstraction, concurrency control, scheduling efficiency, and so on and so forth. And there is always this trade-off between what you really want and the cost of that intent, right? We all want simple, maintainable, extensible, and portable implementation, but each of them can come at the cost of performance. So we really want a solution that can sit on top to help us manage all these technical details as much as possible, because from application developers' perspective, they really care how fast they can get things done. And by fast, I mean both performance and productivity. Among various solutions, task parallel programming, or TPP, has shown great promise to be an effective solution, particularly for irregular workload. And this is because it allows us to capture developers' intention in decomposing an algorithm into a top-down task graph. At the same time, you can delegate all the difficult scheduling details such as load balancing, concurrency control, to an optimized runtime. And you don't have to worry about all those details that are not difficult to program correctly. This is why, over the past few years, we are seeing a growing number of parallel programming libraries. They are all moving toward more and more task parallelism, such as OpenMP's task dependency clauses, C++26 execution control library, TPP, flow graph, and so on and so forth. Now we are going to look into some mainstream asynchronous tasking programming model and their limitations. In C++, we can create an asynchronous task using std_async. And this is a high-level standard library facility for you to launch a task asynchronously. Let's take a look at this example. Here I have a function compute that does nothing but return its function argument. We use the std_async to asynchronously run this function on a new thread. And that std_async will return a future object for us to wait for this asynchronous task to finish. And we can access its result. In this case, the result will be 42. Very simple. This is an example implementation of std_async. May not be necessarily the optimal implementation, but just an example to showcase how this can be implemented. We have two templates, one on the function type and the other on the argument types. First, we will get a return type of the function using the type trait, and then we create a promise future pair to perform inter-thread synchronization. So the idea behind is basically I promise that I will run your function, and in the future you can access the result from the future object I return to you. Next, we create a thread from a C++ lambda function object that capture the function and its argument using perfect forwarding and so on and so forth, and then we can invoke the function in the body of the lambda function object. Then we detach the thread to mimic the fire and forget behavior of std_async. And finally, we return the future to the caller. With std_async and future, we can build a task graph to handle asynchronous tasking with dependencies. And that is because std_future allows us to perform task-specific synchronization using the wait call or get method available from future library. For example, suppose my task graph has 4 tasks, A, B, C, D. A has to run before B and C. B has to run after B and C. To ensure a correct execution, we need to wait for A to finish, right, before launching task B and C. And similarly, before we launch task D, we need to explicitly wait for B and C to finish. As a result, by properly synchronizing these asynchronous tasks using future.wait, we can create a task graph dynamically. Let's take a look at the same task graph, but implemented using the C++ sender-receiver model, which is a standardized abstraction for composing tasks and dependency in 26 standard. Here, we use a static thread pool to schedule tasks on a pool of worker thread. Then we create a sender task for A and synchronize its execution using the sync_wait method. Before we launch task B and C, we need to wait for A to finish. Okay, so this is the definition of our task graph. Then we create another 2 parallel sender tasks for B and C and use the sync_wait again together with whenO function to explicitly wait for B and C to finish before we can move on to create another sender task for D. Finally, we synchronize task C once more to complete the task graph. This slide shows the same graph but implemented using TPP library with TPP task group, which is a class available in the library for you to create asynchronous tasks and wait for their completion. So first, we will create a TPP task group, TG over here, and then we use the run method to spawn to create 4 asynchronous tasks A, B, C, D. And similarly, we need to use the method wait to wait on A before running B and C, and wait on B and C to finish before running task D. Again, this slide implements the same graph by using OpenMP's task dependency clauses. And we know OpenMP leverages the compiler directives to define tasks and dependencies for parallel execution. Looking at this example over here, inside the OpenMP parallel region, we define the dependency handles in 4 integer variables, AB, AC, BD, and CD, that represent the task dependency from A to B, A to C, and B to D, and C to D, respectively. Then, we can specify the task dependencies using the int and out clauses when creating an OpenMP task. For example, task A has 2 outgoing dependencies on B and C, right? So we need to put AB and AC inside the out clauses. Similarly, for task D, it has 2 incoming dependencies from B to C, and this is why we need to specify BD and CD inside the in clause. So with these OpenMP directives, the compiler is smarter enough to automatically, insert parallel code for you. You don't have to write any parallel code. Essentially, this generated parallel code by compiler will launch asynchronous tasks and properly enforce their dependencies for you. Finally, this slide shows the implementation using OpenSilk, which is a fork join-based programming model that, similar to OpenMP, relies on compiler-generated parallel code using language extension like silkspawn and silksync. In this example, I define 4 free functions to represent the 4 tasks, A, B, C, D. And after running task A from the main thread, we spawn a child thread using silkspawn on task B. And then we continue with the function, the task C, in the main thread. And then we use silksync to explicitly synchronize the execution of B and C before we run the final task D. So similar to OpenMP, like I say, you need a compiler that supports OpenSilk syntax and language extension to run this code. So far, we have seen many different asynchronous tasking models to create task graph dynamically. While each of these libraries has its own, advantage in certain domains, they frequently come with the following limitation that prevent us from fully utilizing the potential of task graph parallelism. So let's take a look at the 4 limitations. First of all, if you pay attention to those models that we just talked about, tasks and their dependencies are often decoupled from each other during the task graph construction, right? If dependencies are not expressed alongside the task creation logic, it's very difficult for a programmer to reason about the task graph structure. More importantly, without a clear dependency structure, you don't give runtime enough opportunities to optimize the task placement and load balancing when constructing a synchronous task, simply because it has no idea about which task is going to be its successor or predecessor as part of a dependency constraint. The second limitation goes to the correct placement of the wait call or synchronization call is completely left to programmers. Well, that means programmer must determine a correct synchronization order at a very fine-grained level. And in the worst case, the number of synchronization using future.wait, the method, will be equal to the number of dependencies in your graph. And when your graph becomes very large, this can become very, very, very messy. In practice, many applications, they do only care about the completion of the entire task graph instead of intermediate tasks. That also makes such fine-grained synchronization unnecessary, costly, and very, very buggy. The third limitation goes to the limited support for building highly dynamic task graph. For those graphs whose structure, dependency, and task content are highly dependent on runtime variables or dynamic control flow result. For example, in this case, OpenMP may not be a good solution because it simply relies on compiler generated static information to reason about your task graph structure. Finally, some of the libraries may require a non-standard C++ compiler to generate parallel code, like OpenMP and OpenSilk, which can have a serious portability issue across different computing platforms. Now, I am going to introduce a new dynamic task graph programming model and system called AsyncTask to address these limitations. Before I talk about dynamic task graph programming, let's first understand the difference between static and dynamic task graph programming, or TGP. All the examples we have discussed so far are basically dynamic task graph programming. In static task graph programming, or STGP, the execution follows the construct and run model. You build a task graph first, and you take the build task graph to an executor and runtime, and it will handle the scheduling detail for you. So you construct the task graph first, and then you run it. On the other hand, in DTGP, the asynchronous task you created can start immediately as soon as layer dependencies are satisfied. So meaning that the task graph construction can overlap with the task graph execution. And for very large task graph, this overlap may provide certain performance advantages over STGP, static task graph parallelism. To better understand the difference, let's take a look at static task graph programming in TaskFlow. This is a C++ library for task parallel programming. Again, using the same task graph for our example, A, B, C, D. A runs before B and C. D runs after B and C. In STGP, using the TaskFlow library, you will need to define these task graph in a TaskFlow object. Then you define 4 tasks in terms of C++ lambda function object, A, B, C, D. And then you use the precede and succeed method to relay the dependencies among A, B, C, D. Very simple. When you finish constructing the task graph, you simply submit it to the executor, and the executor will handle the scheduling detail for you. So as you can see from this example, the construction and execution of the task graph are separate from each other. You construct the graph first, and then you submit it for execution. Instead of starting everything from scratch, we have built our dynamic task graph programming model and system called AsyncTask atop TaskFlow, so we can reuse many of its scheduling facilities. Using the same graph as an example, we can create a task from C++ lambda function object using the silent dependent async method, or the dependent async method if you would like to acquire additional future object that allows you to perform task-specific synchronization. When you create a dependent async task, you can specify arbitrary dependencies using C++ variable parameter pack. For example, when I create the task D over here, I can pass B and C as the last 2 arguments, indicating that task D cannot start until both B and C finish. When you create a dependent async task, like I say, the runtime will start its execution immediately whenever its dependencies are met. So the task graph construction can overlap with task execution. If you do not want fine-grained synchronization using future.wait, you can always use the method wait for all to wait for the entire graph to finish. And this will give you less synchronization overhead, especially when your graph is very, very huge. And you probably already know dynamic task graph programming, DTGP, needs a correct topological order for you to specify dependencies dynamically and correctly. And that is because when you define a dependency on a dynamic task, the parent task of that dependency must exist in a correct topological order, right? In our example, this basically means we can program our task graph using either ABCD or ACBD, because both are correct topological orders. an incorrect topological order. If you happen to know anything about a topological order in your application, then DTGP will not be the right tool for you, because an incorrect topological order will prevent you from expressing a correct dynamic task graph. For example, if you create task D before task B and C, then you cannot specify the dependencies, right? Because task B and C, they are not available yet. So you need a correct topological order in your application in order to leverage dynamic task graph programming. Both method, silent dependent async and dependent async, can take a variable range of dependent async tasks. And this is particularly useful when the task dependencies come as a runtime variable, such as I need to load the task graph from the file, or the task graph needs to be obtained from a return value of the function, and so on and so forth. For example, we can create a vector of dependent async tasks over here, and then we use this vector of dependent async tasks to create another, to specify the dependency when creating another task and using the STL style range operation. Well, you might feel this feature very trivial. Unfortunately, when I'm using existing library, I found this simple feature very difficult to achieve using many of the existing asynchronous tasking library, because their task creation and dependency expression are usually decoupled from each other. For example, if your task graph comes as a runtime variable, such as loading the task graph structure from a file, it is very difficult to do with OpenMP and the C++ standard receiver model. One major advantage of DTGP, dynamic task graph programming, is the flexibility for runtime-driven execution, meaning that you can flexibly assemble your task graph parallelism driven by different runtime variables or control flow results. Let's take a look at an example over here. Depending on the values of the variables A, B, C, D over here, I can create a totally different task graph from my application. If A is true, I'm going to build a task graph G1. If B is true, I am going to build a different task graph G2 and ask G2 to run after G1. Otherwise, if B is false, I am going to create a totally different task graph from G2, G3 over here, and ask G3 to run after G1. Similarly, this can also depend on the task graph structure that comes as a runtime variable. If G1, task graph number 1, has 100 tasks in the graph, I am going to create a task graph G2 and ask G2 to run after G1. Otherwise, I'm going to build a new task graph G3 and ask both G2, G3 to run after G1. This type of dynamic task graph parallelism is very difficult to achieve if you are using static task graph programming, simply because you cannot decide the task graph structure upfront. As you can see from our programming model, AsyncTask does not touch data abstraction. This is a very important decision that we have made based on years of application experience, especially during the early stage design of AsyncTask. We want to focus on coarse-grained task parallelism instead of fine-grained data parallelism, because our goal is to have user describe tasks and their dependency in an expressive and clean graph language. With this interface, users can always describe their function as a C++ lambda function object, and they can capture whatever data necessary or a function argument by themselves. This is basically how std async can be implemented based on the early presentation of the talk, right? The advantage of this decision is twofold. First, users still retain full control over data layout and ownership. And this allows them to optimize data structure and memory layout tailored to their specific application domain. Because the way you want to structure your data, organize your data structure, optimize your memory layout is completely depending on your algorithm, your application. And we don't want to do that. Second, letting users decide how and where to store data keeps AsyncTask very lightweight and non-intrusive, there is really not much need for you to modify your existing data structure in order to parallelize your application that fits into our framework. This is very different from many of the data parallel programming models, such as fast flow, TPP pipeline, that conduct yet another data abstraction requiring user to rewrite your code to their library-specific data abstraction just because you want to gain parallelism. Now, I am going to talk about how we overcome some of the scheduling challenges to support our programming model. Our scheduler is built on top of TaskFlow's work stealing scheduler, which has two levels, task level and worker level. At the task level, the job is to decide which task to enqueue to which worker whenever its dependency is satisfied. At the worker level, the job is to decide which worker to run which task whenever a task is available. So this is a masterpiece of work that has been done in more than 5 years, and I cannot cover all the details in the interest of time. If you are interested in learning more about how this work stealing scheduler is working, I encourage you to check out the original research paper that we published in TPPS. Instead, I am going to focus on how we schedule a dynamic task graph atop this work stealing facility in TaskFlow. And there are 3 major challenges we want to overcome. Number 1 is ABA. Dependency tasks must exist correctly. When you specify a dependency during the creation of an asynchronous task, you must guarantee that dependency point to the right memory location. This is the first challenge in ABA. The second challenge is data race. Because in DTGP, dynamic task graph programming, the task graph construction and execution can overlap and it can happen simultaneously. Multiple workers may concurrently access the data structure of a dependent async task, and we must prevent data race from happening. Challenge number 3 is synchronization. Application can issue both fine-grained and coarse-grained synchronization at any time. So we gotta ensure that synchronization does not introduce too much runtime overhead. Let's take a look at challenge number 1, ABA. So ABA means every time you specify a task dependency, such as the task B depending on the task A over here, that task A needs to refer to the right task A. And this is because in dynamic task graph programming, when task A is created, it may start immediately and finish real quick before you want to use it, right? Now, if task A finishes really, really quick and its resources are reclaimed by its running worker due to optimization like a memory pool or object recycling, then these task A you refer to may not be the original task A you want to specify the dependency. And even though they have the same memory address. So this is a classical ABA problem. To solve this problem, we have introduced a special handle called AsyncTask that basically requires the application to retain a shared ownership of each task needed. And this AsyncTask handle operates like a stu-share pointer to ensure tasks will stay alive whenever they are needed. With this shared ownership, we can guarantee that any specified task dependencies will exist correctly and we will not have the ABA problem. So we solved the first challenge. The next challenge is data race. Because multiple threads may simultaneously access the successor of the task. For example, both B and C at the runtime may want to add themselves to the successor of A, right, when they finish. And A may also want to remove its successors when it finishes. A very simple solution, of course, you can use a mutex to enable exclusive access, but mutex is very, very pricey, especially when you have very large dependency, many dependencies on your task. So instead, we find using the simple compare and swap operation with spinning to enable exclusive access is good enough. And this spinning does not incur that much overhead because in practice, your task graph, most task graph from common applications are very, very sparse. And well, if your task graph is very dense, then probably task graph is not the right solution for your application, right? Because you have too many dependencies. So the final challenge is synchronization. A user can issue both a coarse and fine-grained synchronization at any time during the execution of your graph, such as using the wait for all code from the executor to wait for the entire task graph to finish, or using the fine-grained synchronization method future.wait to perform task-specific synchronization. To synchronize this execution, one simple solution is to use a mutex plus a condition variable, right? So we can notify the application, hey, right now the condition has been satisfied, you are good to go. However, this log-based solution can be very expensive when the number of tasks and number of threads have become huge. So to reduce the synchronization overhead, we have leveraged cplusplus20 atomic variables to perform notifying and waiting operation. So this basically allows much of the synchronization to happen in just user space instead of going across the kernel. And in our experiment, we found by simply doing this, we are able to achieve about 11% performance improvement. With all these ideas, our scheduling algorithm is completely log-free. There is no mutex involved, of course, with cplusplus20. Again, we have published this algorithm in ICCAT 2023, and I encourage you to check out the paper for more details. Now, I am going to demonstrate the efficiency of AsyncTask. We evaluate the performance of AsyncTask on both micro benchmarks and a real-world application to study the performance without and with the impact of application tasks. In terms of micro benchmarks, we measure the performance on 4 commonly used task graph patterns: linear chain, binary tree, embarrassing, parallelism, and random graph. In linear chain, tasks are executed sequentially, one after another. Very simple. Binary tree, this is a very frequently used pattern for implementing parallel divide and conquer algorithm. Each task will spawn 2 dependent tasks all the way to the end. Embarrassing parallelism, all tasks are very simple, independent of each other, and they can run completely in parallel without any dependencies. Random graph, tasks have dependency assigned randomly and arbitrarily, representing irregular workloads. In terms of the real-world application, we use AsyncTask to implement a task parallel static timing analysis application in VLSI, where we parallelize the timing propagation algorithm using AsyncTask. This is the baseline we consider during the comparison: OpenMP tasking, Parsec, OpenSilk, AsyncTask LK, and AsyncTask CD. So AsyncTask LK replaced our scheduler with OpenMP's task scheduler. And OpenMP's task scheduler leverages a log-based hash table to keep track of the tasks and their dependency at the runtime. And this is probably one of the reasons the OpenMP's tasking performance is not so good compared to many of the other libraries. But this comparison allows us to measure the performance of our log-free scheduling algorithm and how good it is. AsyncTask CD replaced our atomic variable-based notification algorithm using condition variable. So we want to see, by using cplusplus20, what could be the potential performance advantage that we can get from the comparison using cplusplus17. All programs are compiled using G++12 with C++ standard 20 enabled and optimization level 03. Machine we tested is a 64-bit Linux machine with 128GB memory and 20 Intel i5 cores, each at 4.8 GHz. To reduce variance, all the data I report over here is an average of 10 runs. This slide plots the performance comparison of the 4 micro benchmarks: linear chain, binary tree, embarrassing parallelism, and random graph. And in general, as marked in the red square line, we can see AsyncTask is doing a pretty decent job. It outperforms the baseline in nearly all scenarios. For example, if you look at the random graph over here, as we increase the number of tasks, as we increase the size of the graph, AsyncTask scales much better than the other baselines. And the gap to, for example, OpenMP continues to enlarge. On the right-hand side over here, where we measure the performance at a fixed graph of 2 million tasks across different number of threads, we can see the runtime decreases as the number of threads increases. And it's saturated at about 4 to 8 threads. And of course, this depends on the maximum parallelism available in your task graph structure. So similar trend can be also observed in other 3 micro benchmarks. We also measure the programming productivity in terms of the ease of use of AsyncTask by surveying over 300 graduate students in my HPC course at UW-Madison. I basically took advantage of me teaching high-performance computing, and I designed a programming assignment asking students to complete these micro benchmarks using 5 different DTGP libraries: AsyncTask, OpenMP, OpenSilk, Parsec, and StudAsync. And by the end of this assignment, I asked students to rate each library in a score of 1 to 10, the higher the better. Here's the result of the survey. Most students find AsyncTask, OpenMP, OpenSilk, and StudAsync very easy to learn. And they can complete most programs with AsyncTask and StudAsync. Debugging is a little bit disappointed because in DTGP, everything happens in a very dynamic fashion, but students still find AsyncTask the easiest to debug. This is because the expression of the tasks and dependencies are not decoupled from each other compared with other libraries. In terms of correctness, most students have a hard time using existing library by AsyncTask to complete the random graph benchmark. And this is the message that I deliver in the early of the talk. Especially for OpenMP, we found 90% of the students cannot get it right. Okay. Now, I am going to talk about the evaluation on a real-world application that we collaborated with NVIDIA and EDA company. And this application is called Static Timing Analysis, or STA. And STA, you probably knows about. STA is a very, very important step in the overall design flow of your VLSI and digital circuit because it verifies the timing behavior of your circuit. Basically, we want to ensure the time can arrive, every signal can arrive on time for the given clock frequency. We implemented the task parallel STA algorithm using AsyncTask, where the timing propagation is modeled as a dynamic task graph that propagates the timing data, such as arrival time, slew, delay, constraint value, and so on and so forth, from the inputs of the circuit all the way to the output of the circuit. For example, here I am showing you a task graph that represents the timing propagation of a very simple circuit that has only 5 gates, 1, 2, 3, 4, 5 gates. We evaluated the performance on 4 industrial circuit graphs: AES Core, DeskPerf, BJ-LCD, and Leon2. These are all open source benchmarks available in the VLSI design automation area. The largest task graph we evaluated on the benchmark has over 4 million tasks, and that's about 8 million dependencies. It's very, very large. As you can see from this plot, AsyncTask always outperform the baseline, regardless of the number of threads you use to run your task graph. There is always a consistent gap between AsyncTask and others. And this result basically highlights the efficiency of our log-free scheduling algorithm. We also compare the performance with STGP, static task graph programming, implemented using TaskFlow. So the purpose of this experiment is to highlight the advantage of DTGP, especially for large task graph, where overlapping the task graph construction and execution can provide a certain performance advantage. We know in STGP, building a task graph is typically done in just one thread, and that does not overlap with the task graph execution. For a large task graph like this benchmark DGLCD, which has about 400K tasks and dependencies, the time you spend on constructing the task graph is non-negligible. It's taking about 15% of the total runtime. Well, in this case, DTGP will be about 9% faster than STGP. Obviously, when graphs are very small, then the scheduling overhead of DTGP will outweigh this overlap advantage. In today's talk, we have understood the importance of asynchronous tasking with dependencies, and we went through some of the mainstream asynchronous tasking programming library and talked about several limitations of those libraries. Then we introduced a new dynamic task graph programming model called AsyncTask to address this limitation and showcase some of the high-level ideas how we overcome the scheduling challenges to support our model. Finally, we demonstrated the efficiency of AsyncTask on both micro benchmarks and the real-world application. Everything we discussed today about AsyncTask has been integrated into the open source TaskFlow project. In case you don't know, TaskFlow is a header-only C++ library that is built completely from standard C++ facility. There's no dependency on external library. And TaskFlow is a library for you to program task parallelism, and the project started in approximately 2018 to help Department of Defense in the US to parallelize critical circuit design automation challenges that cannot be efficiently handled by existing model. So basically using AsyncTask is very, very easy. You simply need to download the TaskFlow project and compile your program by telling your compiler where to find the TaskFlow header file. That's it. No wrangling with installation. Finally, I would like to say thank you to all the people who are using TaskFlow in their project. And TaskFlow is open source and it's being used by a great number of people. We have many industrial use cases such as AMD, and recently I happen to know Roche is a company on bioinformatics. They are also using TaskFlow in their system, and we are always happy to collaborate. The project will not be successful, of course, without the sponsors, and we really appreciate the financial support. With that, I am going to stop here, and I will be happy to take any questions. Thank you very much. So since this is recorded, if you have any question, please stand in front of the mic.
Yeah, great talk, thanks. Is it possible to pass data between tasks explicitly in there, or do you have to use something like pre-declared shared variables?
You need to do this by yourself because we do not touch data abstraction.
Okay,
Yep.
Thanks.
This is a library focusing on task parallelism instead of data parallelism.
Got it.
Hi, thank you for your talk. Actually, following up on that question, is there a way to mark memory to be shared between tasks versus memory that's best passed between tasks, or is that just on the developer?
This is based on shared memory architecture. So by default, we assume you have a shared memory architecture.
Thank you.
And you can always capture the data by reference using lambda function object. Then you can access those data whatever you want.
Yeah, thank you. And the second part of my question, are tasks always single-threaded objects, or can they be themselves parallelized, like partially parallelized? If, for example, like in your example, when you have 20 cores, like if a task is using 4 cores and then you have 4 tasks running or 5 tasks running in parallel?
So in our model, we assume each task needs to run atomically, meaning that each task is run by a single thread. If you want to explore more parallelism inside your task, you need to decompose your task into several another tasks.
Okay.
Yeah, so you need to explore another level of parallelism.
All right.
Like creating another task graph from the execution of the task and so on and so forth.
Okay, thank you.
Hope it makes sense.
Yeah, no, that made sense. Thank you.
Hey, thanks for the talk. I'm just curious, how does it handle exception if a task throws
Handle
One.
what? Sorry.
Exception.
Exception. That's an excellent question. In fact, handling exception is a very tricky thing in a parallel computing environment. We do have facility for you to handle exception. You can do exception in coarse-grained level and fine-grained level. In fact, this is a collaboration with AMD when they are using our project. They want us to support exception. And eventually we decide to separate the exception to 2 levels, and you can handle exception at a very coarse-grained level, such as you wait for the entire graph to finish, and then you can capture the exception whenever there's an exception being thrown from a task. Or by using dynamic task graph, parallelism, or the programming model in AsyncTask, you can acquire the future object that will automatically populate the exception thrown by a task to user. So you can capture exception at 2 levels.
Would it be possible to identify which particular task produced that exception with that approach?
Yes. We do have a facility that allows you to identify which task through the exception. Because eventually, exception will be stored as a pointer per task. And you can always handle that or post-process it after your task has finished.
Thanks. I assume it uses STD thread, not STDJ thread. Is it cancelable?
Yeah, this is cancelable. You can cancel the task graph at any time you want.
Does it use top source, or how do you handle
Actually,
it?
by the way, when exception happen, the task graph will be canceled automatically. So we will not continue to propagate all the error all the end to the completion.
Thank you.
Thank you for the talk. I just want to ask, are we able to check the kind of closed loop dependency at a compile time?
Closed loop at compile time?
Yeah, closed loop dependency at a compile time.
I'm not sure what you mean by closed loop.
It's kind of like A depend on B depend on A, and the C depend on B, and A depend on C. It's kind of cycle, yeah, cycle loop dependency.
So in dynamic task graph programming, AsyncTask, we do not support that because one of the motivation is you can separate the definition of your dynamic task graph outside the control flow. You describe your control flow outside the task graph, and then based on the dynamic control flow result, you can explore different task graph parallelism. However, in task flow, if you are using static task graph parallelism, we do have a very spatialized interface that allows you to integrate a control flow into the task dependency. And that is one major difference between task flow and existing library.
Gotcha.
So it goes beyond the traditional DAG-based model, which prevents you from expressing control flow in the graph. So it can express end-to-end parallelism.
Thank you. And another question, say if we want to pause the task, do we know at which kind of node it stopped, or like which group node it paused?
You mean you want to pause
The entire
task in the middle of its execution?
It's kind of I want to pause the entire task graph execution, right? I want to know kind of at which node it paused. Is that possible?
Right now, we do not support pausing tasks because we believe that is something that needs C++20 using coroutine. But many of our users are from industry. We cannot just, they are still using C++17. It's very difficult for us to say, hey, right now I want to support coroutine. I am going to migrate everything to C++20, and then we will lose a lot of people use cases. But yes, to your question, pausing a task is possible, but that brings another topic of using coroutine to enable multitasking within a task.
Sounds good.
But right now, we do not support that.
Gotcha. Thank you.
Sure, thank you very much. Any questions? Other questions? And thank you for all the excellent questions, by the way. I also learned from many of you.
You talked a bit about the, companies and stuff or projects that are currently using this project. Could you go into more of those details and what they're using it for, and other use cases that
we have summarized all those use cases in our website. For example, one of the motivating application of task flow is circuit design automation. This is a application that we want to design software method to help people design integrated circuit, like cadence, synapses, software, and you can probably imagine today's designing those circuits is very, very computationally expensive. We often need to deal with billions of transistors, like NVIDIA's Blackwell GPU has billions of transistors. So handling those problems demand a lot of computation, and part of the challenge is very irregular. And I show everybody the example in the early slide. We have this task graph, very, very irregular. So we really need some sort of task parallelism that can support execution of task graph to better handle those irregularities.
Right.
But we also have some other application from like computer graphics. This is something that out of my expectation, since the project was originated from design automation area, but later on when we open source the core, we realized many people are downloading the project for computer graphics. They are implementing task flow they are implementing their rendering engines using task graph.
Right, okay. That's
I'm
also
not
not my
asking in
area.
that area, I don't know.
Right, okay. Yeah. And are there any other, I guess, use cases of, I guess, like these topological graphs that come up in, various engineering problems that you think could benefit?
I think as long as you can describe your application in a task graph, you can benefit from it.
Right.
Yeah. But the bottom line is the irregularity. If your application is primarily data parallel or demanding a lot of data parallelism, then do parallelism using OpenMP will be the right tool for you.
Right, okay.
And the memory saturation, saturating the memory bandwidth will be the primary optimization goal if your application does not have that much dependency.
Right, okay. Thank you.
Okay. Any other questions? If no, thank you very much again for coming to my talk. I will be sticking around to answer any more questions if you have. Thank you very much.